Hi, my name is Brandon Lipscomb, and today I will be solving this problem. The problem statement is as such. Water is pumped from the large tank shown in diagram A below. The entrance to the pipe section is sharp-edged, and the pipe is cast iron with a total length of 2.0 meters. Flow within the pipe is observed to be fully turbulent. The relationship between volumetric flow rate and actual head rise is provided in the pump specifications and is shown in diagram B. A. Determine the volumetric flow rate for the system. B. Show the observation of fully turbulent flow was correct. C. Is the pump 70% efficient? Determine how much power must be supplied to the pump. Okay. Now, we're going to start with A. Volumetric flow rate, Q, equals velocity times area. Okay, area is pi over 4, pipe diameter squared. Okay, and velocity here, let's pick 2 points so we can do the Bernoulli's. Point 1 is at the top of the container. Point 2 is at the exit of the pipe. All right. The velocity at point 2 is the velocity we're looking for because it has the diameter, and velocity up here is really going to be 0 because with a large container, when it drains, the relative velocity of the top is going to be close to 0. So this is get subscript 2. All right, let's write out Bernoulli's equation, which is P1 over density times gravity plus velocity 1 squared over 2 times gravity plus Z1 plus head rise of the pump equals pressure 2 over density times gravity plus velocity 2 squared over 2 times gravity plus Z2 plus head loss major plus head loss minor. Okay, we can simplify this further by saying that P1 equals P2 equals P atmosphere, because both point 1 and point 2 are open to the atmosphere, therefore their pressures are going to be the same. We can cancel those out. Okay, like I said before, at the top of a large container that's draining, the velocity is going to be close to 0. So we can cancel that out. Z1 minus Z2 equals 6 meters. We're given that right here. Okay. Head of the pump added is going to be 20 minus 2,000 Q squared. Okay, which we can sub in V2 times pi over 4 times pipe diameter squared for Q to get 20 minus 2,000 multiplied, I guess I'll just write it underneath, is V2 times pi over 4 pipe diameter squared, and that is squared as well. So this is multiplied by this. Okay. Head loss major equals the friction factor times total length over pipe diameter times velocity 2 squared over 2 times gravity. This can be found on page 411 of the Fundamentals of Fluid Mechanics textbook, 6th edition. I will be using this textbook as reference for this problem. Now the equation for head loss minor is the sum of the loss coefficients times velocity 2 squared over 2 times gravity. And this can be found on page 416. Okay. So the whole point of doing Bernoulli's equation is we're trying to find velocity 2 at the exit so that we can solve for the volumetric flow rate of the system. In order to do that, we can only have one unknown. Right now we have 3. So we need to solve for both the friction factor and the sum of the loss coefficients. So first, we're going to solve for the friction factor. Okay. And to do that, for fully turbulent flows, the friction factor is a function of relative roughness or equivalent roughness divided by pipe diameter. Okay. This can be found on page 412. So in order to solve for this, we first need to find the equivalent roughness for the pipe. And it says right here that it is cast iron, and the equivalent roughness for cast iron is 0.26 millimeters, or 0.00026 meters. Remember, there's 1,000 millimeters per meter, so I just divided by 1,000 to get this in meters. Okay. Now we want to find the equivalent roughness divided by the pipe diameter. So we're going to do that right now. 0.00026 meters divided by the pipe diameter, which is 0.07 meters. Okay. Put this into the calculator. And this gives us an answer of 0.000371. Okay. Now I'm going to use the chart or the diagram on page 412, which just relates friction factor as a function of equivalence or equivalent roughness over diameter. And it looks like it's about a quarter of the way up between 0.02 and 0.04, which would put the equivalent rate, the friction factor, 0.00371. It would give the friction factor of 0.025. Remember, it's a quarter of the way between 0.02 and 0.04. So a quarter of the way up is going to be 0.025. Okay, so now that we've found the friction factor, the last thing we have to do before we can solve Bernoulli's is we have to find the sum of the loss coefficients. Okay, now there are two loss coefficients. One is the sharp-edged entrance, and then the other one is the exit. Okay, and then so we're going to find both of them and then add them up for the sum of the two. Okay, so KL sharp-edged entrance equals 0.5, which can be found on page 417 of the textbook. Flip the page over, and KL of the exit equals 1.0, and this can be found on page 419. Okay. And I found that using figure 8.27, which is loss coefficient for a sudden expansion, which an exit is a sudden expansion. And the table looks as such: 1, 1. This is A1 over A2, and this is KL, the loss coefficient. Okay. A1 is the pipe. Okay. Okay. A1. A2 is the entire space that it's going into, which is endless, or you could say infinity. So A1 being a number and A2 being infinity, this goes to 0, which would put KL at 1. Okay, so that's how I found the loss coefficient, was using figure 8.27 for a loss coefficient for a sudden expansion. Okay, so now we add up the sum of the loss coefficients, being 1 plus 0.5. We get 1.5 there. All right. Let's see, I need another piece of paper. Okay. Ran out of space on this paper, but we're going to put it on this paper now. So let's rewrite Bernoulli's. Okay. Rewrite Bernoulli's. Okay. As Z1 minus Z2 plus HP equal velocity 2 squared over 2G plus head loss major plus head loss minor. Okay. Now we're going to plug in the equation for head loss, for head gain of the pump, which is 20 minus 2,000 Q. And we're actually going to sub in V2 times pi over 4, pipe diameter squared. This is all squared. Okay. Being that it is 20 minus 2,000 Q squared. Okay. Now, on the other side, we'll have velocity 2 squared over 2 times gravity plus major being F times length over pipe diameter times velocity 2 squared over 2G. And then the head loss minor being the sum of the loss coefficients times velocity 2 squared over 2G. Okay. Now we're going to plug in 6 meters for Z1 minus Z2 plus 20 minus 2,000 times V2 times pi over 4 times the pipe diameter, which is 0.07 meters squared. The entire thing is squared, equals velocity 2 squared over 2 times 9.81 meters per second squared, plus our friction factor, which is 0.025, times total length, which is shown right here to be 2 meters, over pipe diameter, which is 0.07 meters, times velocity 2 squared over 2 times 9.81 meters per second squared, okay, plus the loss coefficient, or the sum of the loss coefficient, which is 1.5, times velocity 2 squared over 2 times 9.81 meters per second squared. Okay. Okay. This becomes 26 meters minus, do the math on the calculator. So minus 0.0296 V2 squared. Okay. See better? Sorry. Equals do the math on the calculator. 0.1274 velocity 2 squared. Okay, plus 0.0364 V2 squared. Okay, now we're going to solve, we're going to put all of the V2 squared terms onto the right side and then solve for V2. Okay, 26 meters equals 0.9134 V2 squared. Which gives us V2 equals 11.595 meters per second. Okay. Now we can use the first equation, Q, volumetric flow rate, equals velocity times area of the pipe. And area of the pipe is just pi over 4 pipe diameter squared. Sub in our new velocity we just found. Multiply it by pi over 4 times the pipe diameter, which is 0.07 meters squared. Okay. Solve it on my calculator. Okay. Volumetric flow rate is 0.045 meters cubed per second. And this is our answer for part A. Okay. Part B, they're asking us to show the observation of fully turbulent flow is correct. Now, fully turbulent flow must have a Reynolds number greater than 4,000. Okay, so that's what we're looking for. The equation for the Reynolds number can be found on page 413, which says the Reynolds number is equal to the density times velocity times pipe diameter divided by the dynamic viscosity. Okay. Now on table 1.6 on the front cover of the textbook, you can find that for water at 15.6 degrees Celsius, density is 999 kilograms per meters cubed, and dynamic viscosity is 1.12 times 10 to the negative 3 newtons times seconds divided by meters squared. And with these two, we can solve for Reynolds number. 999 kilograms per meters cubed times velocity 2, which is 11.595 meters per second, times the pipe diameter 0.07 meters. okay? Divided by the dynamic viscosity, 1.12 times 10 to the negative 3 newtons times seconds divided by meters squared. Okay. Put this in my calculator, solve for Reynolds number. Okay. The Reynolds number turns out to be 723,962. Okay. 0.8125. This Reynolds number is significantly greater than 4,000, which means the flow is indeed fully turbulent and that is a good observation. Okay. Now for C, they're asking us to find if the pump is 70% efficient, determine how much power must be supplied to the pump. Okay. Yep. Now this equation can be found on page 666. Power required equals density times gravity times volumetric flow rate times the head added of the pump over the efficiency. Okay. Let's first find the head added by the pump equals 20 minus 2,000 Q squared. Now we know that Q is 0.045 meters cubed per second. So we can actually find the head of the pump at this point, being 20 minus 2,000 times 0.045 meters cubed per second. Okay. 0.045 squared times 2,000, 20 minus. Okay, it gives head of the pump equal to 15.95 meters. Okay. All right, now we've already said, so we can start plugging things in. 999 kilograms per meters cubed times 9.81 meters per second squared, 0.045 meters cubed per second. Head of the pump, 15.95 meters, all over 0.7, okay? Okay, and this gives us a required power of 10,048.695 kilowatts required for the pump. And that is our answer to part C. Okay. My signature. And again, I'm Brandon Lipscomb. I solved this problem.
Yeah, it works.